It's my pleasure to introduce Professor Gianluca Occhetta from the University of Trento. He's going to talk about siesta actions and birational geometry.
Thank you. It's my pleasure to be here. Well, actually, this morning I checked with Roberto and I gave my first talk here in Complutense in 2009, and this is the fifth one, so I feel at home here. Okay, so my plan for today is, in the first part of the talk, to give an overview on sister actions and the relation with birational geometry. I've been working the last few years a lot on those topics, mainly with Solá, Conde, Eleonora, Romano, and Jarosław Wiśniewski. So many of the things that I'm saying are done with them. So, but after a general introduction, I will then focus on a recent result, which uses tries to use sister actions to attack a special case of campana-Peternel conjecture. Okay, so what's our setting? We start with the smooth complex projective variety and a sister action. So let me give some terminology and basic results on the action. So when you have an action and you pick a point in X, either the point is fixed or it moves in a one-dimensional orbit. And when you close it, you get a rational curve. In particular, X is uniruled, so if we stick to the Picard number 1 case, we are dealing with Fano manifolds. And if it's not a fixed point, then we have two limits of the orbit, and they will be called the sink and the source of the orbit. I'm just trying to introduce some terminology. And a nice thing about working with smooth varieties is that the fixed point locus is again smooth. So this is very good thing to work with. So we can take the fixed point locus and we decompose it as a union of smooth connected components. And if we pick a point in a fixed component, we can look at the induced action on the tangent space at X, but also at the induced action of the tangent bundle restricted to the fixed point component. And there is a very nice decomposition. I mean, the tangent bundle of the fixed point component is a direct summand of the restriction of the tangent, and the normal splits into two bundles, which corresponds to the orientations of the actions. I will try to explain it more clearly later, but it has a positive and a negative part, which corresponds to the weights of the action because the weights on the action of the tangent would be 0, and this is the tangent of the fixed point component part, positive and negative, and this gives a global splitting of the normal part. Okay, these are just the runs. And an important result. Wiśniewski is probably the father of this theory, and so let's look at what are the Wiśniewski cells and the Wiśniewski decomposition. So we pick a fixed point component, Y, and we look at points whose orbit have limit in Y, either the sink or the source. So in improper terms, say points going to the right to y, and points we are going to the left to y. So in this representation, we have this cell. So points whose source is in y and points whose sink is in y. And these subvarieties are locally closed, are affine bundles over the fixed point component, and X can be decomposed as a union of the plus cells or the minus cells. And from this decomposition, I put here just a part of the theorem, but from this decomposition, it follows that you also for instance, the homology of the variety can be computed from the homology of the fixed point components, taking into account the ranks of the normal. So this decomposition provides also a decomposition in homology, for instance. What is not this decomposition is not a stratification, meaning if you take the closure of a cell, what you get is not a union of cells in general. Okay, and well, among the fixed point components, there are two specials, which are the ones which contain the sink or the source of the general orbit. Or if you want, the ones for which the closure of the BB cell is the Hall variety. And these are called the sink and the source of the action. And then the action has a unique sink and a unique source. And possibly many other fixed point components that I will call inner. Well, and you can go from every fixed point component to the sink or to the source by a chain of closure of orbits. And so, well, we can also consider the orbit graph, which is not in general a complete graph, by taking as point the fixed point components and edges. We put an edge if there is an orbit linking to components. Okay, so let's look at some examples. Probably the easier one is the following. We take the projective space and we pick an action which has weight 0 on some coordinates. So now we do nothing, and we multiply by t the other coordinates. What happens? Well, this action has just two fixed point components corresponding to the linear spaces defined by the vanishing of the first block of coordinates or by the vanishing of the second block of coordinates. And these are the only fixed point components. And the orbits, well, if you take a point which is not in these two linear spaces, you take the unique line passing by the point and meeting the two linear spaces, this is the orbit. Well, this is the closure of the orbit. Okay. Let's take a slightly more complicated one. Here I'm putting 3 weights. So you see that the first coordinate is multiplied by t, the second by t minus 1, and the other one are fixed. So here we have 3 fixed point components, 2 points, and 1 codimension 2 linear space. But I don't like this action on the projective space. I will explain you later why I don't like this. But I like its restriction to a quadric. So let me restrict the action to this quadric, which is invariant. And then on the quadric, I see the 2 fixed points and the intersection of the linear space with the quadric, which is a smaller quadric. So I will explain later why I like the action on the quadric and I don't like the action on the projective space. Because we will introduce a nice property of an action which the restriction to the quadric has and the original one has not. And another one, we start from an action as in the first example. For simplicity, I fixed n, so n equal to 5 and 2 planes. Okay, so we have seen how the action works. And now I want to consider the induced action on the Grassmannian of planes. So I'm looking for the invariant, not the fixed planes, but the C-star invariant planes. And I have 4 types. Well, the sink is a fixed plane, so it's invariant. Then I have planes which are spanned by a line in the sink and the point in the source, or a point in the sink and the line in the source, and finally the source. So this action is like this. It has 4 fixed point components. So when we pick a point in one P2 and the line in the other, the component would be P2 times P2. So the 2 inner components are P2 times P2, and then we have 2 isolated extremal fixed point. Sink and source are points. Okay. Now, let's put in the picture also a line bundle. So we will pick usually an ample line bundle on X, but how is this related with the action? We need to choose a linearization of the line bundle. What is a linearization? Is an action on the total space of the bundle which is compatible with the action that we have on X. And moreover, it's linear on the fibers. And it's a general fact that these linearizations exist, so not a problem to find one. And what happens at the fixed point? Well, at the fixed point, the fiber of the line bundle is invariant. And the action on the fiber is just a multiplication by an integer, by a character. Okay, this character is called the weight of the line bundle at that point. The important thing is that if you are in a fixed point component, the weight is the same for every point. So actually, the weight is a property of the whole fixed point component, not of a particular point. It doesn't change. So we talk about weights of the fixed point components. And well, up to a normalization, the minimum and maximum values are achieved at the sink and the source. And up to a normalization, we can assume that the value in the sink is 0. So we have 0, then increase in values, and the maximum will be the one in the sink. So in a way, with the help of the line bundle, we can put some order on the components. Well, and in the case of Picard Z, it doesn't matter what line bundle we choose, but if the Picard number is higher, different linearizations may give different orders on the component, except the sink and the source. Okay, so we have the weight. We can regroup the fixed point components according to the weight. There may be more than one with the same weight. And these weights are called the critical values of the action. And the number of different weights plus 1 is called the criticality of the action. And well, there is also another invariant of the action, which is the maximal weight when we normalize at 0. But okay, so this is now the picture. We can order the fixed point components according to the weights. sink and source are unique. For other values, we may have more than one. Okay, so now this is the property I was hinting before. What does it mean for a sister action to be equalized? Equalized at the fixed point component means that the weights of the normal bundles at that component are just, well, there are positive and negative weights, but are just +1 and -1. Or in other words, if you look at the orbit who has sink or source in the component, the isotropy subgroup of the action is trivial. So, I mean, we don't have some 2-to-1 map or 3-to-1 map to the orbit. No, the C star has just the star goes injectively in the orbit. And this is a very powerful property. With this, we can prove many interesting results. For instance, if the action is equalized, the closure of the orbits are smooth rational curves, and their degree with respect to a line bundle is just the difference of the weights. Okay, so now come back with me for a moment to the example of the projective space with 3 weights, the -1, the 0, and the 1, which was point, linear space, point. This action is not equalized. And an easy way to see it is by using this lemma. Because, well, the weights are -1, 0, and 1. So if it were equalized, a line connecting the sink of the source and the source would have degree 2 with respect to L. But it's not. Well, a line has degree 1. So the action is not equalized. Somehow, for the action, that line is a double line. It's not equalized exactly on that orbit. But when we restrict to the quadric, well, that line is no longer there. And so the action on the quadric is equalized. Okay. Now, okay, these are the sister actions. And what about the birational transformations? Okay. To have birational transformations, I need the action to be spatial, but not as spatial as we will see in a moment. The action is called of B type if the sink and the source are divisors, codimension 1. But if they are not, no problem. We blow them up and they become codimension 1. Because the action, if the action is equalized, it lifts well to the blow up. This is one of the other nice features of equalized action. If the action is not equalized, the blow up is not going to have an action. You may do a weighted blow up depending on the, it's much more complicated. But if it is equalized, just do the old fashioned blow up and you get an action with sink and source, which are divisors. Okay, and the idea is that if I have an action of this kind, so 2 divisors, the action is defining a birational map between the 2 divisors, between the sink and the source. How? So I need some definitions, but if you look at the pictures, basically, let me take the inner fixed point components and all the BB cells to the left, which are the ones which are marked in green. I'm taking all the inner fixed point components, all the BB cells to the left, and I'm closing them and intersecting with the sink. This is the Z0, which is there. And I do the same on the other side, so I get the subvariety of the source. But outside of those two subvarieties, there are no reducible cycles going from the sink to the source. So for every point in y0 minus c0, there is just one orbit going out and landing on the source. So this is the birational map. The isomorphism is take a point inside this bed locus, follow the C star, and you will get the image. And then, I mean, to define it, we have to take out all the BB cells, smaller BB cells, but it may happen that the map is still defined on some bigger locus. Probably we will see an example. But okay, the point here is that we have a birational map. So stupid case. If there are no inner fixed point components, this is an isomorphism. So basically the X is a P1 bundle. So not very interesting. So let's see an example of a non-trivial birational model. Let's go back to the example of the action on the Grassmannian of planes in P5 induced by the action on P5, which had two fixed planes. So here the fixed points are 2 points as sink and source and 2 copies of P2 times P2. Okay, this is not P-type because the point is not the divisor of the Grassmannian, so blow up the sink and the source, and we get 2 projective spaces of dimension 8. Okay, then let's look at the where is the map not defined. If we take the BB cell on the left, starting from the orange one, there is just one orbit coming out of each point. So this is going to cut the P8 in a second. What about the next one? Well, then the orbit coming to the left from the green one are cutting the P8 in the second variety of the second. And so what is the birational map? Is a birational map which blows up the Segre and contracts the strict transform of the secant on both sides. This is in this case we get the same map going from the left to the right and from the right to the left. But somehow, well, the action gives you a picture of what is happening. You see this green exceptional divisor contracting and becoming the P2 times P2 and on the same on the other side. And well, this one is a spatial quadric transformation. It's composition of a blow up and blow down, and all the spatial quadric can be realized in this way via sister actions. Okay. So this was sort of the general introduction. So what can we do now? So in this slide, I will tell you what can we do, but I'm not going to talk about it today, and then we move to the more specific topic. So we have this birational map. One question is, well, in this example, it was a blow up, a blow, and a blow down. In general, how can we factor this birational map? And well, there are at least two ways that we tried and we studied. One is by taking via the GIT quotients of the actions, meaning that you have your action, you fix a value in between two weights, and essentially you cut there. You look what orbits you are seeing there. That is a geometric quotient. Well, this is, but the idea is that. And so you have a lot of geometric quotients. One, for every two weights, you have one quotient in between. And this map can be factored by blow up, blow down, passing by all the geometric quotients. And this is one thing, but okay, now we know about the strong factorization conjecture. So can we find a better factorization? Can we do all the blow-ups first and all the blow-ups next? And this is related to the study of the Chow quotient of the action, meaning a space parameterizing all the possible cycles, all the possible ways to go from the sink to the source. So the general orbit is one point, but if you have reducible orbits, well, you may have the same orbit and then different ways to go. So somehow you want to separate all of them and get a parameter space for all these one cycles. Well, and the Chow quotient provides a factorization of this map via blowing ups and blowing downs, not smooth. Well, we had an example in which the Chow quotient is not smooth, so it's not that we weren't able to prove it. It's smooth in the particular case in which the tangent bundle of the variety is Neff. Then we can do blow-ups, smooth blow-ups and smooth blow-downs. If someone knows, as a special case of Chow quotients of sister action, one can get the spaces of complete collineations, of complete quadrics, of complete skew forms, which are usually described starting from the projective space and blowing up things. Is exactly what happens here. We will have actions whose sink is a point, we blow it up as a projective space, and then the BB cells are giving the stratification that you have to blow up to obtain these spaces. Okay, and other possible related problem. Well, if you want the inverse point of view. Okay, you have a sister action, you have a birational map. But if I give you a birational map, can you produce a sister action such that this is the associated map? So we did some work on this for spatial Cremona transformations. Not only the one of the projective space, but the one studied by Fu and Wang from the projective space to a fan of picker number 1. And well, we were able to explain how to construct these realizations. And another thing that I'm doing now with Solá Conde and Lorenzo Barban, which was a former PhD student of him, is try to construct geometric realization for a special kind of maps. So pick a Mauridrian space, pick two contractions of the Mauridrian space. Well, targets are birational. So there is a birational map between the two. Can we find the geometric realization of this? Well, it seems that the answer is yes, and that the variety on which you construct the action is again a Mauridrian space. So, I mean, there are many open questions and many paths starting from these ideas. Okay, but what are we doing now? I would like to explain a way to deal with a special case of the Campana-Peternel conjecture. Campana-Peternel conjecture, we will see it later, but basically says that a Fano manifold with numerically effective tangent bundle is a rational homogeneous variety. Okay, and in order to get there, I will start with this section classifying actions with small invariants, so small criticality, few fixed point components. and with a twofold purpose. One, to show how to use the birational map to do this. And then, because I will need it for the Campanale-Peternel problem. Okay, so easiest possible thing, criticality 1. Criticality 1, well, it's not so interesting. But if the sink and source are points, then you can have just P1. If one is a point and the other is positive dimensional, you can show that you just have point hyperplane in Pn. So nothing special also here. A bit more interesting is if both the sink and the source are positive dimension. Well, we blow them up, we get a B-type action without inner fixed point component, so a P1 bundle. So the two blow-ups are isomorphic, but then this variety has two different projective bundle structure, one on the sink and one on the source. And well, there are not so many varieties around with this property. So this is linked to this, I think, interesting problem to classifying these varieties with two projective bundle structures. But let's now go to criticality 2. And sink source and one weight in between, and let me assume that the sink is a point. So easy situation. Well, and we did this last year, and basically it splits in two cases. If the Picard number is bigger than 1, well, it splits into cases for the arguments which are used in the proof. If the Picard number is bigger than 1, we have two cases, a product of projective spaces or a blow up of a projective space along something. But, well, this is the proof of this goes through Mori theory and split families, that kind of stuff. So it's not really too related with the sister action. I want to give an idea of the proof in the Picard number 1 case. Okay, so we have a variety of Picard number 1, an equalized sister action of criticality 2, and the sink is isolated. Okay, well, the fact that the Picard number is 1 and the sink is isolated means that in weight 1 we can have just one component. It's not so important, but in the picture there is just one component, we cannot have more than one in this case. The idea is deform this action to the trivial action. So we build a smooth fibration with every fiber is isomorphic to our variety, but on this fibration we construct a sister action, which is the original action on over one point and the trivial action over another point. And all well, in between there are no fixed point components. So this is a new action which has one component more, but this is the situation now. I mean, on the left is the original action, and on the right there is one component more, which is the original variety. The original variety which is fixed. Okay. We do our game, we blow up the sink, and now we get a birational map between the projective space and our variety. And, well, in this easy situation, one can show that this map can be factored in a very simple way as a blow up and a blow down, and it's one of the Fu Wang spatial 2-1 transformations. So in particular, from this we get the classification of X. So this is a way to use information on the birational map to get information on the variety. And these are the guys. quadrics, Grassmannians, spinor varieties, other homogeneous varieties, and some linear sections of homogeneous varieties. They all qualify. Well, they all really have a criticality to action with isolated zinc. Okay. And well, just I'm not going to need the criticality reaction, but I just want to say that if you pick a criticality reaction with isolated zinc and source, those correspond exactly to the spatial quadric transformations, Cremona transformations. So this variety can be classified using the Cremona. So, well, up to now, with this bridge between birational transformation and sister action, we have used what we know about birational transformation to get information on the sister action. I hope that at some point we will be able to go the other way. So to use the information on the sister action to prove something new about birational transformation. But for the time being, we just used everything is known about birational transformations to get information on the sister action. Okay, so let's get to the main point. Okay, as I said before, this conjecture is now quite old conjecture of Campanella and Petternen predicts that a Fano manifold with Neff tangent bundle is rational homogeneous. So, rational homogeneous varieties are Grassmannian flag varieties for projective spaces and quadrics, or you can take linear spaces which are isotropic with respect to something, then there are something exceptional, but it's a very nice and understood word of varieties. Okay, what is known? Not that much. If the conjecture is true up to dimension 5, and then there are some scattered results. I mentioned a couple of them. Then there is some, okay, if the dimension is 6 and the Picard number is bigger than 1, but, well, there are some other scattered results, but I will summarize by saying up to dimension 5 and some special situations. Okay, but why should we mix Campanella and Petternen with sister action? Except from the fact that we worked on Campanella Petternen and we work on sister action, but no, I mean there is I think that there is a philosophical reason to which says that this is a reasonable assumption, because we want to prove that a variety is rational homogeneous. A rational homogeneous variety has an affine algebraic group acting transitively on it. So it has a very big terms acting on the variety. So to assume the existence of a very small terms, I mean, it's somehow going in the right direction, philosophically. Well, we can do with just the tangent Neff, we are not. So let's pick another feature of the homogeneous and add it to the assumption. Okay. Well, okay, so first idea, great, but the fixed point component are smooth. The restriction of the tangent splits nicely. So also the fixed point component have Neff tangent bundle. So let's do some inductive argument. But the problem with the fixed point component is that they are fixed. So there is not the action anymore. So if we want to use the assumption on the action and use induction, we have lost the action. Well, I don't exclude that we can do something in low dimension, because if we take X of dimension, I don't know, 6 or 7 or whatever, the fixed point component would have dimension at least 5, so be rational homogeneous. I don't exclude that something can be done, but I mean, it can be done for, okay, so assume you prove it for 6, but for 6 add the sister action. When you go to 7, you cannot use the inductive step because in the fixed point component, there is no sister action. So, well, I don't recommend this approach, but so how can we use the nearness of the tangent? Well, this is the great question, whoever approaches this conjecture, but the usual answer is look at the rational curves, because the nearness of the tangent implies the existence of nice families of rational curves. Well, families which are unsplit, covering, and with smooth, the family is smooth, and the evaluation morphism is smooth. So you have a nice diagram of the family of rational curve in which everything is smooth. And we call such a family a beautiful family. Because, well, actually, what we assume is not the nearness of the tangent, is the existence of a beautiful family. But clearly we don't know if we suspect that it is the same at the end, but well, at least we just assume what we use is the existence of this nice family of rational curves and an equalized sister action. Okay, so if you pick a curve parameterized by the family, well, you can move it with the action, and it's going to another curve in the family. So essentially, you have an action also on the family. And you have an action on the family, you have an action on the universal family, and with not that much work, you can show that also these induced actions are equalized. So they are nice actions. Okay, and what are the fixed points in the family? So what does it mean that a curve, a point is fixed in M if the corresponding curve is an invariant curve? So either is fixed or is the closure of an orbit. Okay, so here bridge means is the closure of an orbit, because otherwise the statements were becoming too long. And if we pick a curve which is not invariant, well, we have an orbit in M, so we have two limit curves which are invariant curves. So we can pick any curve and move it until it becomes either fixed or the closure of an orbit. And well, by studying these actions, we can prove there is nothing really deep in the proof of this theorem, just a careful study of the induced action. Well, that the action is particularly nice. So the weights are all proportional and are all proportional to the degree of your line bundle on the family. So 0, D, 2D, whatever. For every weight, you have a unique fixed point component, so not more than one. And if you take a fixed point component, you can go to the next or to the previous with the curves in the family. The orbit graph is complete, so you can connect any two components with an orbit, and the decomposition is a stratification. Just this, by putting together the action and the nice family of rational curves. So, well, which I think it's nice, but what about CP? So we are not proving that a Fano manifold with Neff tangent bundle and an equalized sister action is homogeneous. Would be too good. We assume something on the action. We start, well, looking at the small criticality cases, we see that the easier are the ones in which the sink of the source is a point. So we said, okay, let's start with this. So we assume that we have a Fano variety of picker number 1 with F tangent bundle and an equalized sister action whose sink is a point. And this is enough to prove that these are homogeneous. In particular, but this is a posteriori, what are the rational homogeneous varieties with an action of this kind are exactly the Hermitian symmetric spaces. So these are the guys. But I mean, prove that the variety is rational homogeneous, that similar action on rational homogeneous varieties are well understood. So you can just go through the list and look and okay, these are the guys. Okay, so the point is, how can we prove that X is homogeneous? Well, basically, we will prove that if we the lines passing by any point, I mean, these are the fibers of the evaluation which is smooth. These are smooth varieties. We will prove that those varieties are homogeneous. Then we will use not so old result, but not wording, not the VMRT, not the embedded variety in the projective tangent space, just the fiber of the evaluation. Okay, because so pick a point which is fixed by the action. Pick the family of, let me call them lines, if they are not lines, but the family of rational curves passing by that point. And there is an action on this. And what are the curves which are fixed by the action? Well, the orbits going to the left, the orbits going to the right, and the curves staying inside. So we have a criticality 2 action on this MY. The source, the sink is points corresponding to curves going to the left, middle components if there are curves contained, and source curves going to the right. But if we start with related extremal fixed point and we look at the first component, there is just one curve going to the left. So the action on the family of rational curves will be of criticality 2 with one isolated extremal fixed point. So we have the classification. So we have the classification, and this is in principle what we have. We don't like some cases, and with some ad hoc argument and a bit of legwork, we can throw out essentially the non-homogeneous. And then it's almost done, because now we have the new list of candidates in which everything is homogeneous. If the Picard number is 1, all of these have been proved to be rigid under Fano deformations by Wang and Mock. So if we have 1 in our fibration, which is this, all the varieties are like this. There are not rigidity results for the product to projective spaces, but well, we show that all the fibers are going to be projective spaces, but via a different argument involving families of rational curves. So now we have the evaluation map of the family in which all the fibers are isomorphic and are rational homogeneous varieties. And together with Luis and Jarek, we had this theorem when we worked a while ago on the Campanar-Peternel conjecture that in this case the variety is homogeneous. So it's enough to show that, well, it's not a work to show, but it's enough to show that you have a nice family of rational curves and all the fibers of the evaluation are homogeneous. And so we get that the text is rational homogeneous via this tray. And I'm stopping here.
Questions?
Yeah, I think it's not possible, but it is of the possibility of making terms of high dimension flux.
Well, not yet, but I always, because I had the same question this summer by Cinzia Casagrande, and we said, okay, we should think of that, but we didn't have time to think. Yes, because, I mean, if we start with the bigger torus, worst case, we can downgrade it and have everything we have for the sister action. But if we look at the one sister action, then on the fixed point component, we will have the other part of the torus acting. Yes, it's something which makes perfect sense. Well, at least, but sooner or later we will try.
Okay, then no more questions. Then thanks the speaker again.